His vision strengthens Argo Anglic's reputation as a trusted partner in the international energy and industry sectors. So I welcome on behalf of the organizers, and the stage is all yours, Dr. Pavel. Please. Can you please transfer the control to Doc Sir?
Good afternoon. Can you hear me?
Good afternoon. Yes, you are audible.
Yes, sir. Yes, sir. You are audible. Can you please start sharing your screen?
Yes,
Okay. You are visible and audible, sir. Please make it presentation. Yeah.
Can you see my screen?
Yes, sir.
Perfect. Thank you very much for this kind introduction, sirs. Good morning, or better said, good afternoon, ladies and gentlemen. Namaste from Europe. Greetings to the Indian hydrogen and composite community. I'm honored to be here today, although remotely, to make a presentation, but I will do my best to come and visit you next time. India is a great country, great people, and India has a very promising future. Thank you for giving me the opportunity to share some information about large volume, lightweight Type 4 composite tanks in MEC applications. The Argo Anlik company and the group is split into 3 smaller companies, and one of them is the Argo Anlik Tank Systems company, which is located in the west part of Germany at the border to Netherlands. And we mainly provide different hydrogen technology solutions. Our products can be mainly clustered in 5 categories. One is the project engineering related to hydrogen plants, electrolyzers, then the fuel cell systems, filling stations, also e-generator. We engineer hydrogen gas components like valves, gas handling units, TPRDs. Then also storage system, which is the 4th cluster, especially for heavy duty vehicles and off-road vehicles, for example, for mining. And the focus today is on this storage in MECs. We call it H2 tank container. I will later on a little why. And the Type 4 composite tanks. Just about me, but you can find me on LinkedIn. I'm originally from Berlin, Germany, from the capital. I'm from the background aerospace engineer with the focus on lightweight structures, especially with composites. This is how I came to the tanks and the composite pressure vessels. I'm expert for Type 2, Type 3, and Type 4 tanks. I've engineered many Type 4 tanks and built production lines globally. We see many initiatives worldwide towards hydrogen economy. One of these initiatives currently also takes place in the center of Europe, along the Rhine River, which is on the west side and also then to the border to the Netherlands. And especially the large logistic companies push the shipping companies to decarbonize their container ship to enable 0 emissions on the Rhine River. And for this, the decisive part is, of course, the efficient storage of hydrogen energy. And this is defining the real success of this economy. The problem is that the hydrogen infrastructure is very fragmented, not only in Germany, but I think everywhere. So this is the driver for MECs. MECs is staying for multi-element gas containers. They offer mobility, scalability, flexibility. But why are MECs so important for hydrogen storage? Because they can bridge this infrastructure gap. They can be transport and storage system in one. They are modular and scalable, but you need to make them modular and scalable. They are ideal for international and multimodal logistics, and they can be used as onboard storage for powertrain like fuel cell, but at the same time, they can be also used for the gas transport of dangerous goods. And of course, automatically, they are becoming an enabler of early hydrogen markets. At Argo Anleg, we engineered and built a specific type of MEG. We call it hydrogen tanktainer, H2 tanktainer, which is a registered trademark here in Europe. This tanktainer is built of 8 very long Type 4 tanks. There are many integrated features like controller unit, Wi-Fi, GPS, shock and angle sensors. Just to highlight some current ongoing projects where we integrate this kind of solution into real applications. On the left side, this is the shipping application, which is more common on the river. Depending on the fuel cell system, if it's a 400 kilowatt or 1.2 megawatt, basically there is a need for more storage of hydrogen, so we can integrate 8 or 4 of those tanktainers. And very interesting project coming up also in Europe is the integration into trains. On the right side, you can see there is a huge system for the fuel cell application, and behind the storage of the gas in a modular system, H2 tanktainer. A small comparison between common concepts of MEGs. We distinguish, I personally like also to distinguish, I worked many years in the automotive, and we distinguish purpose design and conversion design. The purpose design rethinks and reshapes technologies to make it fit for this real application. And this is this right one. The conversion design is you take something available, you adapt and integrate available technologies into an existing architecture. Has also benefits. Just a comparison, what are the main differences? Of course, the main differences is the tank integration. In this left side, which is called the conversion design, you usually integrate the tanks in a vertical position. But you need to have a lot of tanks you need to integrate. For example, the number of tanks is 50 or 54, depends of course also on the size, but usually you have multi-tanks there. The problem is you have a lot of single components, you have complex pipe routings, you have more connections which are increasing the risk of ignition, and especially for shipping, where the society is very, very careful using hydrogen, you have ATEX zones, which are the explosive zone protection throughout the entire system. On the right side, when we look at the purpose design, we have the horizontal integration, we have long tanks, we can store a bit more hydrogen, we have reduced single components, and this kind of system can be made also stackable. We have less connections, which reduce the risk for ignition, and the ATEX zone is only at the front and the back side. So this makes them possible to be stackable. To make a complete MEG, you need to have different components. To have a really holistic, safe-oriented MEG, the structural frame on the left side is important, needs to have a specific approval. You need really to pass very strict tests. You need to obtain a CSD approval. On the right side, you can see the bearing system. We used here hexagon. Then, of course, we need to have large volume Type 4 tanks. We use 8, more than 2,000 liter per tank, 500 bar. And then you have a number of BOP components. Each tank has a safety valve. We have each tank has a TPRD, vent lines, GPS, Wi-Fi, shock, and angle sensors. Just an idea to show the major assembly steps coming from the frame. The alignment and welding of the frame is very important to keep the precision and the tolerances. Then the bearing system you see here in the middle, and then you integrate the tanks. High precision is required because the space is limited. You cannot exceed the limits outside. So high precision and exact alignment during assembly and welding is really required, because small errors can lead to distortion and fitting problems and make the tank integration impossible. What is it making integrated and smart? Well, the modular design, the plug and play, which are the plug and play modules with standardized interfaces. It can be easily integrated to ships, which are already used to containers. Then we can use this as an integration into refueling infrastructure with this quick swap system. You bring in this container, you change it with a filled one. You can also use it as a mobile hydrogen station. And very, very important and interesting part, it's that it has this multimodal transport compatibility. It is suitable for road, rail, and maritime application at the same time. The smart features is related to the built-in sensors, the remote monitoring, GPS, the tank-to-tank communication. And as we are gaining a lot of data, we have a huge database later for AI-based condition monitoring, which is not the case yet. Now the transition to the Type 4, to the composite. I think this kind of session, which is related to hydrogen economy and to composite community, combines nicely this kind of application. Why to use Type 4 tank? Why Type 4 tanks matter for MEX? Well, basically, of course, it is mainly the weight reduction, the high durability of this kind of composite material based on carbon fiber. We have longer lifetime without corrosion issues. We have improved fuel efficiency in transport. The usable hydrogen per payload is higher. It's easier for handling and for the light trailers. And this is bringing us to enable the earlier hydrogen markets. This chart, this plot shows, let's say, the large volume Type 4 tanks, only for hydrogen, not for CNG, only for hydrogen, which has ever been built, plotted against the working pressure. So we see here 4 circles. I hope you can see them. They are not too small on your screen. We see that the largest volumes on the 350 bar and on the 500 bar are on the 2000 liter level. If we go higher to 700 bar, then the highest built volume is something below 400 liters. And there is a concept coming from US, which is already higher than 900 bar, which is storing around hydrogen in 500 liter. If we look at the design space we are getting from regulation, then there is this EN 17339. This allows to design volumes up to 3000 liter and the pressure to 1000 bar. Then there is this ISO 19881, which allows pressures to 700 bar for the design and volume 1000 liter. And then this quite famous long-lasting standard, which is 11119-3. Then we have EN 12245, which allows tanks for the transport of dangerous goods. There is no pressure limit, but there is a volume limit, which is 450 liter. We have this R134 for hydrogen vehicles. There is no volume limit, but a pressure limit 700 bar. And most of the tanks built for Type 4 are scattered in this area below, mostly below 450, 500 liters. This means that there is a new technology coming up, with this large volume Type 4. Because this is something more and more coming in relation with high pressures, it is important to address some major challenges related to large volume. What are the major challenges? First of all, the engineers like to scale, coming from small volume tanks because the budget is usually limited. Then you develop a tank on the subscale level, and then people like to transfer it to large volumes. But this is not a valid approach. It can be done, but this is not a valid approach. First of all, the similitude theory is not valid here anymore. It is very sensitive, so it is necessary to be very careful here. We have challenges in physics, in structural mechanics, materials, and manufacturing because we cannot scale linearly. There is a complexity in design and manufacturing which is increasing for large Type 4. There is the 3D stress distribution of the composite shell, which needs to be well considered. The material behavior and the degradation of the composite parameters needs to be well considered. Then the liner technology and the liner structural behavior, manufacturing tolerances, and also the quality control. Just for this discussion, for this presentation, a small comparison of what I mean with small type 4 tanks and large type 4 tanks. Well, I consider here small type 4 tank liters below 450 liters. Why? Because this is coming from the standard we have already for a long time. They are quite common, and the large type are exceeding 450 liter, going to 3000 liter, and maybe in future more. The typical use case for the small type 4 tank is the onboard fuel storage, vehicles, forklift, and for the large type 4 is tendency more the bulk gas transport. We see, of course, the pressure levels are a little bit different. The design complexity for smaller tanks is a standardized geometry we are familiar with, but the design complexity is increasing with large type 4 tanks. The manufacturing method, quite common, is filament winding. It's still the case for type 4, but it needs a large-scale wet winding process with adapted tools. The cycle time for smaller tanks can be counted in minutes, maybe few hours, but if I wind a type 4 tank, which is a large one, it is going to many hours. It is exceeding one shift. It can be 8 to 10 hours winding. The type certification is quite common, known for the community for small type tanks, but for large type 4, it is more complex because, especially in combination with MEX, it requires a system approach. In order to transfer the small volume type 4 tanks into large volume type 4 tanks, it requires a certain methodology to determine the composite pressure vessel reliability. There are here two rectangular shapes, the red one and the blue one. The red one is basically related to the determination of the state of the stress inside of the structure, which is related to the internal forces as consequence of external force coming from the pressure. Many engineers like to work and appreciate simulations, all kinds of simulation with very nice software, but they mostly work in the red area. But the risk, and to reduce the risk, we need to have a rigorous understanding also of the blue area, which is coming from the load capacity of the material, how to transfer properties from small tanks to large tanks. And this requires really a careful view on it. If both red and blue are well done, we can make a nice assessment. A short comparison of the common structural analysis method. I think the composite community knows. We have the classic laminate theory, which is quite common for thin-walled composite, but it is not sufficient anymore for the thick-walled because the radial stress is missing. I will highlight later. The netting analysis, we know it's a nice approach, but has a limited validity for thick-walled. The 3D elasticity is not quite common for the thin-walled composite. It is complex for the thick-walled, but very, very useful. And finite element calculation, which is well appreciated from the engineers, but still we see, and we are surprised that there are many mistakes done because the wrong elements are chosen because it's coming from the small volume application using 2D shells or axisymmetric models. It requires 3D solid. What it means, I will show you later. I'm not willing to go too much into the details here.
Dr. Pavel,
Yes.
Please expedite last 4 minutes.
Yes, yes. I'm almost done. Yes. I'm not willing to go too much into these details and skip the details. The main message is here. The consideration of 3D elasticity is important, and the consideration of the radial stress. The radial stress must be considered for thick-walled. Here are some effects showing the impact of the radial stress. On the left side, you see a plot where you have the stress distribution along the wall thickness, and you see for the different degree of anisotropy of the material, there is a huge increase on the inner side. And on the right side, you see when I increase the walls, I make it more thicker, so the deviation to common stress, which we know from the membrane, is getting bigger and bigger. Here, a comparison between the selection of different models in FEA. The quadratic thick shell does not cover this 3D stress coming from the radial stress, which is quite common in the simulation still. It requires the quadratic solid elements. Otherwise, you cannot get the effects from the bigger. Coming to this blue part, which is where I would like to recall this important paradox of fibers. Why are fibers so strong? Because they have thin structures. So the likelihood and the probability for material imperfections is very small. Yeah, this is why they are so strong. But if I increase the material volume, there is a degradation in this material property, which I can transfer also on the composite level. If I compare a 200-liter tank with a 2,000-liter tank, so the burst strength, only due to the volume effect, which is increasing the likelihood for defects, is making a big impact here. The comparison also here between the small volume and the large volume is that tolerances we are known from filament winding become more significant and deviations for the large volume, because if I create a huge structure, the impact of defects coming from manufacturing are significant and needs to be well controlled. Something about liner buckling. I think people know in the scene about the liner buckling. There are four major events triggering liner buckling, which is the decompression of soaked hydrogen, the vacuum in the inside of a tank can be a reason, low pressures in combination with low temperatures, and the uncontrolled fiber tension can be a reason for liner buckling. On the left side, there is a chart here showing the effect of soaked hydrogen. Basically, when you have a high temperature condition on the tank and you decrease the pressure very fast, and suddenly you will measure an increase of hydrogen, which is coming from this liner buckling effect, because the hydrogen is collecting between the liner and the composite shell. And if we go now to the large volume, so considering that the liner thickness is relatively small and the liner diameter is relatively large and the Young modulus of the liner material is relatively small and we have high GDT requirements, all this is driving the sensitivity for liner buckling for the large volume tanks. Last two slides, some steps about the liner manufacturing using rotomolding. So this is our mold. On the left side, the liner mold preparation, which is then filled with the powder, the mold closing, and the liner deforming. The liner has a diameter of 750 millimeter. And this is basically the last slide showing the large volume liner in production. And I'm coming to the end. Thank you very much.
It was such a wonderful presentation, Dr. Pavel Novak. We got the insights. I thought you'll be focusing just type 4, which is like a hot topic in the Indian context. But the technology you have taken in the form of vertical and then the horizontal, and the way you have increased the capacities and capabilities because of hydrogen as a fuel of the variety of vehicles, that's your commitment and a good effort to save Mother Earth. Thank you for being the part of this. I mean, giving your knowledge to the next generations. Thank you for sharing all your information, sir. We once again thank you on behalf of organizers. Can I have a big round of applause for this, Dr. Pavel? Thank you,
Sorry,
sir.
say it again.
Thank you, Dr. Pavel, for all the inputs you are doing for Mother Earth and the great works. Please.
I appreciate, and I'm glad to come next time in person and to share more details. I have only 25 minutes You need to give me more time to share more with you, with India. It's a great country.
I'll request you for a lecture, maybe online, offline, whenever you are in India, offline, of course, I mean, in person. And
Yeah,
otherwise,
yeah.
from university, I will try to, I mean, I'll make sure that we have some good interaction time. At least 1 hour, I think, is the bare minimum requirement. Thank you, sir. Thanks for your time.
All the best to you. Bye-bye.
Bye. Okay. Moving on. Next in the series, we have Miss Swapnali Wagh from TUV Rhineland, Mumbai, is a dedicated professional specializing in testing, inspection, and certification services. She plays a key role in ensuring compliance, quality, and safety across industries with strong expertise and commitment. She supports organizations in meeting global standards, driving trust, reliability, and sustainable business practices. So I request Ms. Wagh to please start with her works. And you will be having 20 minutes, ma'am. Not you?
No. She's joining.
Electrically. But now I am
We have to bear for a moment, maybe some technical glitch. Welcome, Ms. Swapnali. We were waiting for you. If you don't mind, I directly hand over it to you. Yeah, I once again welcome Ms. Swapnali Wagh from Mumbai. She is a dedicated professional specializing in testing, inspection, and certification services. And she plays a key role in ensuring compliance, quality, and safety across industries. With strong expertise and commitment, she supports organizations in meeting global standards, driving trust, reliability, and sustainable business practices. So, ma'am, over to you. You have 20 minutes time, please.
Ma'am, can you please unmute yourself?
Am I audible now?
Yes.
Yes, we can see your presentation and you are audible. Please.